2020, que se llevará a cabo del 18 de agosto al 1 de diciembre bajo el tema Diseñando el Futuro. Podrás acudir de forma presencial en la unidad de posgrado de Ciudad Universitaria o seguir la transmisión a través de nuestras redes sociales. Consulta la programación en www.fundacionunam.org.mx/Foro 2020.
De conferencias Universidades por la Ciencia, organizado por Fundación UNAM, el Colegio Nacional y el conjunto de universidades y centros de investigación del Consorcio en México, Estados Unidos, Canadá, Reino Unido, España, Brasil, Argentina, Chile. Les agradecemos mucho el interés y que nos acompañen. Y el día de hoy tenemos una conferencia muy especial a cargo de la doctora Magellan Olinto, quien es la coordinadora, el dean de la División de Física en la Universidad de Chicago, y es profesora distinguida en Astronomía y Astrofísica y en el Instituto Fermi. Y es un placer el darle la bienvenida. Muchísimas gracias, doctora, por aceptar esta invitación. Welcome to the seminar series of the Universities for Science Consortium, organized by the UNAM Foundation, the Colegio Nacional, and the group of universities and research centers in Mexico, US, UK, France, Spain, Brazil, Argentina, and Chile. Thanks very much for following us, and today we have a very special conference by Professor Magellan Olinto. She is the Dean of Physical Sciences in the University of Chicago and is a distinguished professor in astronomy and astrophysics, and also in the Fermi Institute in the University of Chicago. Dr. Olinto has a very distinguished career. She is a specialist in astronomy and astrophysics, studying the neutron stars, and it's an honor for us that she accepted the invitation to present this conference. We are particularly happy because the university, the National University of Mexico, has an office in Chicago, and we have the assistance and the representation by Alberto Fonserrada, by Erika, by Dr. Pulido, who is the chair of the UNAM office in Chicago. And we have a lot of students, Mexican students in the university, and this open us a very interesting possibility. We are joined by the president of the UNAM Foundation, Dionisio Meade, the executive director of the UNAM Foundation, Araceli Rodriguez, and the president of the Consortium for Universities of Science, Dr. Araxi Urrutia. Thanks very much to all of you, and Professor Meade will give some welcome remarks. And thanks again, Dr. Olinto. We're looking forward for this conference. Dionisio, por favor, adelante.
Thank you very much, Jaime. Thank you very much, Angela, por acompañarnos el día de hoy a esta presentación. Nos da una gran satisfacción ver que este programa de Consorcio de Universidades por la Ciencia se va consolidando y que pues son prestigiadísimos conferencistas los que nos están acompañando cada martes, y hoy celebramos mucho la presencia de la doctora Ángela Olinto, que es precisamente el dean de la Facultad del Área de Física en la Universidad de Chicago. Nos da mucho gusto que nos acompañe. Ella, como ya mencionó Jaime, es muy destacada en las áreas de cosmología, partículas de alta energía, en astronomía y astrofísica. Esta idea del consorcio, como lo hemos comentado en sesiones anteriores, pues fue una respuesta que tuvimos frente a las dificultades de tener un contacto presencial con motivo de la pandemia, pero esta adversidad pues se ha convertido en una oportunidad. Convertimos el obstáculo de la pandemia en una oportunidad de intercambio de conocimiento y en intercambio de información, pues contando con la participación de expertos formidables que nos comparten su conocimiento de investigaciones en curso en estas presentaciones de los martes. Hemos subrayado en ocasiones que la pandemia nos dejó algunas lecciones, algunas enseñanzas. Una de ellas es precisamente el respeto a la ciencia y el respeto a los científicos. Hemos mencionado que quienes más respetaron la ciencia en el transcurso de la pandemia son los países que primero pudieron salir de este obstáculo formidable. Y otra de las lecciones que nos dejó la pandemia pues es precisamente el cuidado y el conocimiento del planeta. De manera que una presentación como la de hoy justamente tiene la virtud de acercarnos al mejor y al mayor conocimiento del planeta con una presentación como la que hoy se nos hace. Quiero subrayar que este intercambio de conocimientos con la participación activa de quienes nos escuchan, de nuestra audiencia, tiene también el propósito de ir motivando a muchos de nuestros jóvenes a encontrar, en este caso en la física, pues un campo de desarrollo profesional. Justamente esta posibilidad de conocimiento entre una gente tan destacada como la conferencista de hoy, y que tengan la oportunidad los jóvenes de dialogar con ella a través de las preguntas, de las oportunidades que tienen de este intercambio, pues justamente habrá de motivarlos, creemos nosotros, a encontrar en lo que aquí se nos presente una opción de su vida profesional, de su vida personal, de su vida familiar. Nosotros hemos detectado que quienes tienen la oportunidad de realizar estudios superiores, a su vez quieren que sus familias, sus hijos realicen estudios superiores, de manera que este es un cambio formidable que puede derivarse precisamente a través de estas presentaciones. Quiero comentar para concluir el orgullo que nos ha dado que la UNESCO, en este marco que aquí se ha subrayado, del Año Internacional de las Ciencias Básicas en el Desarrollo Sostenible, haya seleccionado a Fundación UNAM justamente por programas como estos, el de consorcios de universidades por la ciencia o de documentales por la ciencia que se presenta los jueves, precisamente como un mecanismo idóneo para divulgar el conocimiento científico. Y nuestra fundación fue seleccionada justamente a virtud de estas circunstancias para formar parte del comité que se estableció en la UNESCO para impulsar este propósito. De manera que pues, vamos dando oportunidad a que se vaya haciendo y a que se vaya materializando esta oportunidad con presentaciones como la de hoy. Agradecemos mucho por eso la presencia de la doctora Olinto, agradecemos también la presencia de nuestras autoridades universitarias en Chicago y de esta audiencia que aquí ya se ha mencionado, de muchos interesados de distintas partes del mundo que participan activamente en el intercambio que hoy se nos presenta. Muchas gracias a todos, muchas gracias a quienes han puesto a su disposición, a nuestra disposición sus redes para poder realizar este intercambio, y de manera particular agradecemos al Colegio Nacional que se ha sumado a la UNAM y que se ha sumado a Fundación UNAM para poder impulsar este proyecto. Muchas gracias a todos y pues con la mejor ánimo, con la mayor disposición, estamos atentos de escuchar la presentación de la doctora Olinto. Muchas gracias a todos y muy buenas tardes.
Muchas gracias. Creo que posso empezar, ¿no? Entonces, un gran placer estar aquí con ustedes hoy. Soy brasileña y mi español es no muy bueno, entonces vamos a hablar en inglés. Okay, so just to give you a little history, so I am Brazilian from Rio de Janeiro originally, and moved to the US to do my PhD, and have been in Chicago for many decades now, and it's really a pleasure to be able to share some of what we are doing with a wider audience in Latin America, Americas, Europe, anywhere. I will use English because my Spanish, as I mentioned, is not the best, but in Portuguese I could probably handle much better, but in Spanish it will be a slow move. So the theme I wanted to share with you is the new cosmic messengers and their messages. Okay, so I start with this image because I think all of us have seen, I hope, if you haven't, please make sure you do this sometime in your life. Away from cities, away from Mexico City, away from Chicago, go to a place that has beautiful skies, very low level of light pollution. Could be top of mountains, deserts, beaches, places without much light from cities. So some faraway place. And what you will see is something that for thousands of years, humans have looked up and been in awe and in puzzlement of what is it that's going up there? What is the sky about? And today we're so fortunate to have technologies that expanded the view and the marvel that we feel when we look up. We can see a lot more than just what the eyes can show us, right? So in this beautiful image, you will, for those who know the sky a little bit, will notice that there are two cloud-like systems here. So this has to be from the southern hemisphere. Those are the Magellan Clouds. There's obviously a beautiful comet and our own galaxy, the Milky Way. And this is taken in Argentina in 2007, so 2007, during the visit of Magellan Comet. And I like this image. First, it's a beautiful image, but second, it shows different structures, which are, the comet is very nearby. It is part of, it's within the solar system visiting the sun, and that's why you see this beautiful bright tail. You have our own galaxy, which is, where we live, if you think of cosmic scales. And then you see actually tiny little galaxies, which are the furthest you can easily see in this image, which are the Magellan Clouds that I mentioned before. And those are real little worlds. So they're small versions of the Milky Way. Today, with our technologies and the top level of optical and infrared astronomy is the James Webb Space Telescope, which I hope you've seen the wonderful images that telescope is sending us. One can see in a tiny, tiny part of the sky. So this, if you take the moon and you divide it in 10 little slices, this is the size of roughly 2 arc minutes. So this is 1/10 of the linear scale of the moon. And that tiny little place all over the sky, in tiny little pieces of the sky, one can look deep and see a whole history of the universe evolving from its beginnings, which is 13.7 billion years ago, to today. And what this image in particular, which was the first deep image of the James Webb put on their website, shows a cluster of galaxies and lens galaxies behind that cluster of galaxies, which is giving a sense of how you have structures here. And by the way, the big star-looking things are stars, which are very local, but the majority of what's interest in this image is how many galaxies and how far away one can see in the beginning of early galaxy formation. So the first stars, the first galaxies, which is exactly one of the many things that James Webb was designed to do. And the technology to do such a thing took decades of a lot of people's dedication. So it's a huge achievement for all of us in the planet to have the tools to see that deep in the sky. Astronomy and astrophysics have evolved by looking at the sky with not only eyes, optical eyes like we have, the visible light, but also many, many different wavelengths or frequencies, just like in a piano or in any other wave-like system, we have different higher frequencies, lower frequencies, high energies in the language of particles, and lower energy in the language of particles. In astronomy, it has a big, very, very wide multi-wavelength choices. You can observe, for example, the sun in radio waves and microwaves and infrared waves, in visible light, which is what we use our eyes for, in ultraviolet, X-rays, and gamma rays. So these are some of the images of the sun using all these different frequencies. Now, my theme is the other messengers, which are not electromagnetic waves, are not like light. They are particles or they are gravitational waves. So these are what we call multi-messenger observations of the sky out there, or alternative messengers to the electromagnetic waves. So what I described before is the electromagnetic waves here in the middle. And then my work has been focused on the cosmic particles, which basically extend those electromagnetic waves to very high energies, very high frequencies, with cosmic rays, very high energy gamma rays, and neutrinos. But there's also amazing development on the opposite direction. So looking for waves, which are, let me show that again, which are much longer wavelengths than the radio waves that we use radio telescopes for. And that's done instead of looking at the electromagnetic waves of large wavelength, it's actually looking at gravitational waves, which are waves of the space. So it's a space and time are being distorted by events somewhere, and that's how we capture a wave reaching the Earth. And one can make an analogy to hearing what's happening in the universe as opposed to seeing what's happening in the universe. And if you wish the particles at the other extreme, you would be tasting the universe, looking at the actual pieces of matter that reach us with energies which are ridiculously high. And so with all of those messengers that are arriving on Earth, we can make a much more rich view of the universe. Many more interesting questions get posed and answered as a function of time. So let me first do the low frequency, long wavelength observations. Here I put a piece which shows the LIGO detector, and then there are plans for the future with the LISA detector, but also the pulsar timing arrays. These are very large scale observations of what pulsars are doing in space to look for gravitational waves in even larger scales. So let's just remember that one of the most amazing things that happened, and we got to learn about it in 2015, and Barry Barish, Rainer Weiss, and Kip Thorne got the Nobel Prize in 2017 for this amazing discovery. And so this took 50 years of their work, trying to get this kind of event observed. So these are two black holes that coalesce, and as they are getting they merge together. As they're getting very close together, they start distorting. They always distort space, but the closer they are, the stronger these gravitational distortions are. And so the more we can actually observe these strongest waves, the end game of this dance between two black holes. These waves are also generated when two neutron stars are dancing around each other, or a black hole and a neutron star. So anything that has a lot of mass that is being distorted and reaching a different state that really can shake up the distribution of mass in a short amount of time, and that's what we observe the best, right? So these are the two LIGO detectors that are in the US, plus there's Virgo and a few other detectors being built now. That are the original observations, and the first observation of a gravitational wave is from September of 2015. The amplitude of these waves are tiny fluctuations, 10 to the minus 20 fluctuations of space, or of the laser interferometry equipment, which is extended over 4 kilometers to be able to detect this wonderful precise instrumentation. So the LIGO, which is Laser Interferometer Gravitational Wave Observatory, is an amazing achievement, just like what I mentioned about James Webb, another incredible achievement of our brilliant scientists and engineers. So the kinds of things I mentioned, so binary black hole mergers, binary neutron star mergers, neutron star black hole mergers, these are transient energetic cosmic events. We also have gamma ray bursts, tidal disruption events. These are a whole class of events that happen on a human time scale, that we can see things before and after, and things change in the sky. It's not that static universe that we tend to look at, but it's really things, information and evolution, and emitting very high energy gamma radiation, so photons, also gravitational waves, and hopefully neutrinos and cosmic rays out of these amazing events. So here's just a bunch of these different possible types of events, from, flares from black holes and centers of galaxies, the coalescence of black holes, the coalescence of neutron stars, some flaring of pulsars, and then gamma ray bursts and other types of things. And tidal disruption is when you have a black hole and a star go around, and then it gets disrupted by the black hole. So these are all things we observe in these very high energy, and also in gravitational waves and in electromagnetic waves too. Just to close the history of gravitational waves, it began in 2015 in terms of discoveries, and that's called 01. And then there was an 02 and 03 runs of these telescopes, these observatories. And now, because of the pandemic, we had a little delay, but in the next spring, we should be having 04 start, which will be a year run of not only LIGO and Virgo, but also CAGRA. And then 05 would be even longer runs. So these are the things that people are getting ready to do. So these observatories for gravitational waves are distributed throughout the world. And 04 is what's coming. But 03 had 90 events observed. And if you look at this distribution here, we have black hole mergers, binary neutron star mergers, neutron star black hole mergers. And then there are false positives, unidentified, and some terrestrial noise, and events on the mass gap too. So these are very interesting, beautiful science being done with this incredible new messenger. I'll spend the rest of my time looking at the opposite extreme. So instead of the gravitational waves, with the messengers that come with cosmic rays and neutrinos, which is where my work has been focused on. So let's go in that direction. And so let me show you a little bigger image of these multi-messengers. So if you have, for example, a galaxy with a black hole that has a jet, and those jets can be emitting light, and they can also be emitting maybe cosmic rays, maybe neutrinos. It could be the neutron star coalescences in other galaxies that also emit neutrinos and cosmic rays and photons. So these are some of those messengers that I mentioned before at the highest energy. So this is quite puzzling how we get them. We don't quite know the origin of the highest energy cosmic rays, which is the thing we observe with the highest energies of all. The problem for understanding, for doing astronomy with cosmic rays, is that cosmic rays are charged. They are the nuclei of different atoms without the electrons, so they're positively charged. And there are magnetic fields between the sources and us. So they come in a contorted way to Earth. And so it's not easy to know exactly where they started, because pointing back, it ends up in the wrong part of the sky from where it actually came from. So we don't see much in terms of what is the location of these things just by looking back at their trajectories. We need to do something a little smarter to answer the question of the origin of these cosmic rays. So as I mentioned, the cosmic rays are basically the table of elements, and at the highest energies, they do seem to be a mixture of hydrogen, helium, CNO cycle, and so forth. So, as much as we can tell from our measurements. And these are nuclei, meaning made of quarks that are, basically get accelerated to such higher energies. They first get ionized, and then they get accelerated through their charge to very, very high energies. And so they're basically the nuclei without the electrons. We also have electrons and positrons in the cosmic rays, and then we have neutrinos. So the modern table of elements is the table with the Higgs, the forces, the quarks, and the leptons. Those three types of particles plus the Higgs that is recently discovered. And this table of elements is smaller than the big one, the old one. And we observe the photons, which is the electromagnetic electromagnetic force particle. We observe the up and down quarks from the nuclei that come together towards Earth in cosmic rays. We observe electrons, muons, and other things on their way to Earth. And the neutrinos. The neutrinos are the most interesting ones in terms of trying to basically read their messages, right? Because the cosmic rays, the difficulty, as I mentioned, is that they're charged, so they don't point back. Neutrinos point back, which is wonderful. So we could, in principle, see exactly where they come from by just pointing back at their arrival direction. However, they're very hard to detect because they don't interact almost at all. So they go right through the Earth, right through our thumb. Billions come through our thumb every second or so. So they are very abundant, but very difficult to detect. So the techniques to understanding the neutrino origins are the challenge in terms of inventing new technologies and developing that field. So just focusing on how the two get together. So by looking at these types of messengers, there's twice as many cosmic rays. There's twice as many orders of magnitude in the electromagnetic spectrum plus the cosmic ray spectrum. So basically, there's a lot of different information in the cosmic rays. The low energy cosmic rays are likely to be galactic, and the very high energy ones are likely to be extragalactic. And this transition, there's a lot of science being done related to cosmic rays. My work focuses on the highest energy ones because they're the hardest to explain. And the energies reach 10 to the 20 electron volts, which is pretty incredible, macroscopic energies in one tiny little nucleus. So this is the questions we're trying to answer in my research are two. One is the current research, the sources of the ultra high energy cosmic rays, and what are the sources of the astrophysical neutrinos. These are part of what we call astroparticle physics, which includes particle physics, cosmology, and high energy astrophysics all together, trying to understand both the particle physics side of the questions and the astrophysical side of the questions, which is why we call it astroparticle physics. Wonderful. So let me, as I mentioned, cosmic rays it's a very easy spectrum. What the spectrum of cosmic rays look like a power law. It is a surprising spectrum. It's definitely not a thermal spectrum. It doesn't have a temperature. It doesn't exist in one energy scale. It pretty much has a power law distribution through 12 orders of magnitude in energy. There is the lowest energy cosmic rays are influenced by the magnetic field of the solar system. So the sun protects us from cosmic rays at low energies. The Earth protects us also from cosmic rays, which is why cosmic rays at low energies are something very important for folks to understand if humans are about to be going to the moon again, or keep being on the moon. Folks already in the International Space Station, and if we want to go to Mars, we definitely need to understand the consequences of the cosmic ray radiation bath that we will be living in, which is not something we fortunately experience on Earth because it isn't very healthy as far as I can tell. But the origin of those is also the galactic cosmic rays. They just happen to be more protected, so the spectrum turns around. The bulk of the cosmic rays are thought to be produced and accelerated in the galaxy, probably in supernova explosions and shock waves that are produced by those supernova explosions. Then we have a transition to cosmic rays produced outside of our galaxy. We don't know exactly where the transition is, but by the time we get to 10 to the 20, the ones that I care about are definitely outside of the galaxy. So we are looking at something outside of our own galaxy, sending pieces of matter all the way through space from far away to us, and we need to understand where they're coming from. The kinds of experiments we have, some are direct experiments, meaning one can put a particle detector above the atmosphere of the Earth and directly detect the low energy cosmic rays. But for the highest energy cosmic rays, the fluxes are very, very small. So first, if you have a flux of, for example, 0.1 per kilometer per century, sorry, you can't read the century here, which is the kinds of numbers we're talking about. So even if you had a kilometer square detector in space, it would take a century to catch somebody, to catch one of these particles. So we have an alternative way to observe these things, and I'll explain that to you. But it's really a very rare event for these very highest energy cosmic rays. While the low energy ones are very common, so it's easy to detect it. Well, it's not easy, but it's the flux is high enough for us to be able to study them with smallish detectors from meter cube type of volumes, which it's quite significant to put that in space, very expensive, but at least it's doable. While for the very low energy, the very high energy, very low flux ones is very difficult to do. Fortunately, we can observe them and we can study them indirectly. The way we do this is that one of these cosmic rays are so energetic, they reach the upper part of the atmosphere, they interact with the atmospheric molecules, and then they generate a shower, which is very similar to what happens in CERN and in Large Hadron Colliders. When you have particle collisions, you basically create a lot of daughter particles, children particle, and they multiply. So one of such event one particle can create hundreds of billions of particles by the time they reach the ground. This is what we call an extensive air shower. And the way we can observe these extensive air showers is either by putting a sequence of detectors on the ground that detect the particles created by the shower, or we can actually observe light emitted from this shower. The light can be infrared, the light can be ultraviolet, not the James Webb, the opposite extreme, ultraviolet photons, which are accelerated by the shower. And basically, the particles in the shower, electromagnetic part of the cascade, basically interacts with the nitrogen in the atmosphere, and the nitrogen fluoresces. That fluorescence is something we can observe in the ultraviolet, and it's equivalent to observing a light bulb in the UV moving at the speed of light through the atmosphere, many tens to hundreds of kilometers away. We have technology to actually see these things as they evolve, which is a beautiful thing we can do. Or we can be basically looking below the shower, either for the particles directly or for the Cherenkov emission, which is beamed towards the shower axis in the direction of the shower. So you could observe that on the ground too. And so here, just to give you a sense of what these kinds of extensive air showers look like, if you have one proton at 10 to the 14 electron volt at 17 kilometers up, as this shower develops, the number of particles reaches a peak and then it dies off. The particles on the ground are distributed here. The top panel on the left-hand side is following the shower as it develops. The light here is the light as a function of altitude from somewhere between 15 and 20 kilometers down to the ground. There's a peak in production of particles, and we can see that as brightness of the emission of the nitrogen fluorescence. And then we have on the ground, from the core of the shower to the edge of the shower, in this case, 1.5 kilometers from the core, a lot of electromagnetic emission, which is in red. So these are E+, E-, and photon particles. Then we have muons. So a lot of muons that get created do not decay into electrons. They keep on going. They are highly energized, and they can come through and basically are the second largest components. Then we have hadrons, neutrons, and so forth. So those are the components of the shower we can detect. The two largest detectors or observatories for these kinds of particles are the telescope array in the US, which is a 700 kilometer square array with three fluorescence telescopes. So the array on the ground plus the fluorescence telescope to see this light from when it's dark as it develops in the atmosphere. But the array on the ground is measuring 24/7 these showers as they reach the ground. And then the Pierre Roget Observatory, which is the one I participated in, which is the one in Mendoza, the state of Mendoza in Argentina, 19 countries collaborating, including Mexico, and we have 3,000 kilometers square of detector array, 4 fluorescence telescopes. So here's what it looks like. So this is an earlier me, much younger, around one of the particle detectors, which is a water tank with basically 3 photomultiplier tubes and very self-sufficient unit with solar panels, radio antenna, and the particles go through the water. They emit Cherenkov light in the water, and we can see what is happening through those tanks. And each of the tanks are in this, there's 1,660 tanks distributed over 3,000 square kilometers in the area around Malargüe in Argentina, in the Pampas Amarillas. And let me just make a nod here to many of the institutions in Mexico involved in this. Obviously, there's institutions in Brazil, Argentina, the US, all of, lots of European collaborators, but since we are being hosted at UNAM, I wanted to make sure the credit to the Mexican collaborators go here. And then we also have fluorescence telescopes. These are telescopes that look like normal telescopes, meaning they are closed during the day. They open at night when the sun is down and the moon is out of the way. And we can then observe the atmosphere above the array, looking for these showers that develop in the ultraviolet. So with those two types of techniques, one can do a really good, precise measurement of these cosmic rays. And here is one of those productions, one of the results from this huge effort of starting in 2004 and up to now, collecting data, but 2008 onwards with the full array. Here is in black the spectrum of Auger, the Pierre Auger Observatory, and the telescope array in this sort of greenish hue. So what one can see, this is the spectrum of cosmic rays multiplied by the power e to the 2.7. So this power law is the power law that you saw in the original cosmic ray plot that I showed. So by multiplying by that, this power of energy, basically we make most of the galactic cosmic rays pretty flat up to the knee. And then you can see that there are little features. There's a second knee, there's an ankle, and a turnaround. And we think that certainly after the ankle, these things are extragalactic, but we don't know exactly when the transition happens. So here's the same type of spectrum, but now only Auger. And so spectrum multiplied by the third power of the energy, and then you can see the other ankle here, the other knee, the ankle, and the die-off of the spectrum, which we think now is probably due to the maximum energy of the sources that accelerate these cosmic rays. There's also an effect of interaction with the microwave background and other backgrounds from the source to us, since these things are crossing very, very large scales, which is called the Gzk effect, or the Greisen-Zetzep-Kuzmin effect. But the shape and the composition of these cosmic rays, here is a plot that shows the shape of the spectrum, but also the different flavors of the nuclei that we seem to be observing, basically changing flavors as we move from the ankle to this drop-off. And this is more consistent with the idea that the sources have a maximum energy that for protons around 10 to the 18.5 or so. So this is one of the discussions in the field, but basically the jury is still out. We still don't know exactly what the sources are. Some of the favorite candidates right now are starburst galaxies and active galactic nuclei, and more data should be able to resolve some of these questions as we move forward. So switching to the other topic, while I have still some time, is what are the sources of the astrophysical neutrinos? So as I mentioned, cosmic rays are wonderful. They are not super hard to detect. They are hard to detect at those very highest energies, but they are, doable. Neutrinos, I mentioned, are better in the sense of astronomy. They can point back to where they come from, so you don't have to infer their origins through some other means. But the difficulty is actually measuring them, because they go right through the Earth, they grow right through everything. So we need to make a little effort to catch them. So I mentioned the interaction with the microwave. So this is a spectrum of the cosmic neutrinos, or neutrinos that we expect to exist in the universe. Some we know for sure exist. Neutrinos, for example, produced by the sun. Neutrinos produced by a supernova in 1987A. Reactor neutrinos, background neutrinos, atmospheric neutrinos, which is the bulk of the neutrinos that we experience, and those are atmospheric. They are basically neutrinos produced by the cosmic rays that hit the atmosphere. They do these showers in all kinds of scales, and they produce neutrinos through the showers too. And then there are astrophysical and cosmogenic neutrinos. There's also a cosmological neutrino background at the lowest energies, and that cosmological neutrino background is something that we haven't observed yet. It would be lovely to see it. It would be sort of the partner of the microwave background, which is the photon cosmological background. But this is all the flavors of, simplifying the view of cosmic neutrinos. The interesting ones from my point of view is the cosmogenic ones, which is the ones we expected to see exactly through the interaction of the cosmic rays with the background. So a proton interacting with the microwave background produces photons and neutrinos, and through their basically loss of energy, which is one reason for the spectrum to turn around. But the flux of these neutrinos seem to be much harder to detect than this plot would indicate, which is it's a lot lower in flux than we expected a couple of decades ago. And the reason it changed, one of them is exactly because Auger is observing that the cosmic rays at the highest energies are not just protons, they also have all kinds of other components. And that makes the neutrino production not as high. And then we have astrophysical neutrinos, which are neutrinos produced by the sources directly that we should be able to observe. Now, on a detour, just to remind everybody that the solar neutrinos, the supernova neutrino, and the atmospheric neutrinos have already generated great particle physics results, which is the reason why these astroparticle connections are so important, is that we can also learn about neutrinos themselves. And those were 2 Nobel Prizes, one on the solar neutrinos in 2002, and another in 2015 on the neutrino oscillations using atmospheric neutrinos and solar neutrinos. And these gentlemen represent those efforts. One beautiful image that I like to show, and I put that on the original plot when I put the sun in many different wavelengths. I also put the sun in neutrinos, which is a measurement that that Super K, made in this image here for us, which is really a beautiful image. So we can even image the sun in neutrinos. So the goal is to really try to start using the atmospheric neutrino, the astrophysical neutrinos, which go after the atmospheric neutrinos in energy, take over from the atmospheric neutrinos as they die off. And the best detector observatory so far to actually see those astrophysical, the first ones and the ones currently seeing it, but there's many, many efforts to have more observatories that see astrophysical neutrinos, is IceCube. IceCube is a kilometer cube of ice, basically instrumentation around Antarctic ice in the South Pole. So you have the South Pole with a lot of ice above the bedrock, and those detectors that I'm going to show you here, if I can change, there we go. So here's IceCube, not too far from the South Pole, and there's strings of detectors, and you can see basically this hole here with the digital optical modules coming down. And the idea is that a neutrino would then go through the rock, so through the Earth, interact in the rock of the Earth, produce a muon, for example, a muon neutrino would, and that would generate an upward going passage of a muon, which has Cherenkov light emitted, and that's what you see in the IceCube. You can also see this cascading type of event, so it could be crossing through or having an interaction in the ice and then making a little shower, a local shower, which looks like these blobs of events. And since this is a kilometer cube, one of these events is bigger than or of the scale of a football field or a soccer field. And I put Maracanã, which is the one from my hometown of Rio de Janeiro. So that's the size of the events that one neutrino can make in this kind of detector. And again, we want to understand what are these neutrinos. It's likely that they are from some of the same transient energetic cosmic events. There's evidence to connect at least some of the neutrinos that IceCube sees with blazars, flares, which are supermassive black holes in centers of galaxies in far away, most of them, making some interaction, some flaring, and that flare is emitting those neutrinos. It's very likely that a neutron star coalescence will emit a lot of neutrinos too, and those are the ones that we would love to follow up. So putting everybody together in this one slide, we have basically at the highest energy, so this is the field that we work on. So if you get 10 to the 20 electron volts or 10 to the 11 GeV, giga electron volts, you have the spectrum of the cosmic rays here, the Auger and telescope array, and a little bit of Cascade coming down. We have the neutrinos detected by IceCube in yellow, and the blue here is the gamma rays coming from gamma ray detectors and Auger. So the gamma ray Fermi telescope, and then there's basically Auger limit over here on this side in blue. So we expect, because of this, the highest energy cosmic rays, the fact that these cosmic rays exist and they are extragalactic, they will produce these neutrinos and they will produce photons at lower energies because of their propagation alone. So just by having these propagate through, they will generate what we call cosmogenic neutrinos and cosmogenic photons on both sides. But we haven't been able to observe none of these cosmogenic productions yet, which is, and the fluxes are too low for current technologies. So what we're trying to do is develop technologies that go further down and can look at the actual astrophysical neutrinos produced by sources and the ones produced by cosmic rays on their way here. So what we've been leading here at Chicago are two plans to approach this topic. One is the space observatory that we call POEMA, which stands for the Probe of Extreme Multi-Messenger Astrophysics. This was funded by a NASA study for a conceptual design, given the Astro 2020 prioritization for astronomy in the next decade. And what we showed is that we could really build two telescopes within the $1 billion upper limit of funding to observe ultra-high-energy cosmic rays and neutrinos at the same time. So we would look with two telescopes down towards the ground to look for the fluorescence emitted by ultra-high-energy cosmic rays. At the same time, we could observe towards the limb of the Earth, or just below the limb of the Earth, neutrinos which are crossing the Earth at very high energies and making showers on their way upwards. So we would see downward going showers and upward going showers. And to prove that this our conceptual design works, we've been developing many different telescopes that we are flying either in balloons or in the space station. So we had one flight, EUSO SPB-1, which stands for the Extreme Universe Space Observatory on a superpressure balloon. We flew the first one in 2017, and we're getting ready right now to fly the second one next March. So we're integrating the payload, and it's two telescopes, one for the neutrino type observations with Cherenkov emission, and one for the ultra-high energy cosmic ray observations with fluorescence looking down. So we have two telescopes, one for each technique. The space design actually has both of those in the same telescope integrated into one camera, but we thought it was easiest to do both separately for the sort of test flights to show the two techniques independently. And here's SPB-1 being on launch date back in 2017. So again, the principle is simple, right? So instrumenting very large areas like Auger and telescope array do is a lot of work. And if we want to scale this to much larger volumes of the atmosphere, it's easier to do from space. You can go to space and basically look at very large volumes of the atmosphere, looking down for precise ultra energy cosmic ray measurements with two eyes. That gives you more information than with one eye alone. Or you can point the two telescopes towards the limb of the Earth. So for example, if the telescopes were flying here, it would be about 525 kilometers altitude. On the Chicago area, it could be observing all the way past Mexico for both the cosmic rays in between us and Mexico and the neutrinos upward going from the ocean in this case, just below the limb of the Earth. And so this would be quite significant in terms of the volume that we can observe at the same time of the atmosphere. And as I mentioned before, the EUSO program is a long-standing one. We've been developing these telescopes to look at the fluorescence, and now we are adding the Cherenkov telescopes to our program towards this POEMA plan in 2030. We currently have a small telescope, small version of our telescope in the International Space Station, looking at the backgrounds from the ISS down to the ground. And it's been a wonderful time. This collaboration, the GEM-USO one that's providing these balloons and the POEMA design also has participation from Mexico and UNAM. We have Gustavo Medina Tanco, who's been a great collaborator for a long time, and the national PI, but many other institutions also participating. And we have about 16 countries in EUSO. Here's some images of EUSO SPB-1. So once you spend a lot of time and money in people's brains putting a beautiful telescope together, you hope this guy does a good job and releases it when the balloon goes overhead. These balloons, when they're inflated, they're also the size of a soccer field. They're very, very large. They're filled with helium, and they're super pressurized to be buoyant and basically stay at the same altitude of 110,000 feet, or 33 kilometers above the ground. And the idea, we launch it from New Zealand. The idea, and there's a parachute you can see here in the bottom. Once the mission is finished, there's a release, and the parachute hopefully brings your telescope down without infinite damage. But the idea is that it can float and basically follow the winds on the southern ocean. So here's if the winds get to these altitudes above 30 kilometers or so, you can get winds which are very stable and circular around the pole, around Antarctica, and that reach 100 kilometers per hour. So in 4 days, you go from New Zealand to, say, Chile and Argentina, and then back around. So the hope is that we could stay afloat for a long time, 30 days, 50 days, 100 days, as long as possible. So we can basically do most of the work a space mission would do, but from a balloon to prove that we can actually detect both the cosmic rays and the neutrinos. So we're getting ready to launch USO SPB2. They're the two telescopes I mentioned, one looking for fluorescence and the other looking towards the limb of the Earth, above the limb to look for Cherenkov emission from cosmic rays, and below the limb of the Earth to look for tau neutrinos that cross the Earth, produce a tau lepton, and emit this air shower on their way out. We have incredible technologies, cameras on both sides, one that takes pictures every microsecond, and on the Cherenkov side, a camera that takes picture every 10 nanoseconds with new technology of silicon PMs, and multi-anode PMTs on the fluorescence side. Here's some of the team members at different stages, one with the Cherenkov, the team with the Cherenkov camera doing field tests. Another picture is of the fluorescence camera doing field tests. These are in Utah, that we take the telescopes and then we put lasers and LED lamps to check that everything works according to plan. Here's a picture of the camera and images of our collaborators through the mirror of the telescope and the laser trailer that has lasers that we use to test everything. So in conclusion, we've been developing, not only us, but the whole field, but in our case, these two projects, telescopes that can see very, very high energy particles, these new messengers. We use the Earth atmosphere as the particle observatory, and we want to discover the origin of the highest energy cosmic rays, which are above 10 to the 19 electron volts in the case of these two telescopes, and above 10 to the 16 electron volt neutrinos, which are generated by, we don't know exactly, but we expect to be these most energetic events in the universe. And with that, we can use these kinds of messengers to understand new astrophysics and new physics of the particles themselves. Thank you so much. I'm going to stop by showing the launch. And if you want to have questions, you can start putting the questions to me.
Many thanks for that fantastic talk, and really nice image of that balloon going up. Well, that refers to the first question we have, is why is it that neutrinos cannot be detected at normal temperatures? Why do they need to be detected in ice-covered areas or at high altitudes in the atmosphere?
Good question. So let me find my slide. Whoops, I lost everything. Let's go to the right place. So why is it so hard to detect neutrinos? Let's let the guy launch. There we go. He did a good job and he seems happy, you see. Yep, he's happy. All right, so let me find the neutrino plot, just to give you a sense, right? So neutrinos, if you look at the particle tables, just let's remember what a neutrino looks like, right? So we have 3 flavors of neutrinos, and neutrinos are tricky because the things that we know about nature, so we know a lot about nature. The big questions in cosmology are the dark energy and the dark matter, but in terms of the matter we know to accelerate, this is the picture, right? We have the forces, the Higgs boson, the leptons, and the quarks. So neutrinos, here are 3 of the 4 forces, right? So we have electromagnetism, which is the force carrier, the photon. We have strong interactions, which are the gluons, and then we have the Z and the W, which represent the weak force. And on top of those 3 forces, you know, I put the Z and the W together, we have also gravity, right? So neutrinos don't have charge, so they don't interact with photons, so they don't have electromagnetic radiation. they also don't have color, which is the glue, what the quarks have in the electron. The quarks have the color, sorry. The electron, just by comparison with let me put back the color in. Let me start with the neutrinos. So neutrinos don't have charge, so they don't have electromagnetic forces. The others, the electron, muon, tau, and the quarks all have charges, so they all interact with the electromagnetic forces. So all of the red and the top layer of the green can produce light. Neutrinos do not produce light. These are the ones that don't produce light. Then, if you think about strong interactions, is the gluons, and that's only the quarks that have those interactions. Now, the weak interactions, in principle, everybody can have that. And so that's how neutrinos get produced in the sun, is through the weak force that is generated in the nuclear reactions at the center of the sun. So neutrinos can be produced by all kinds of interactions as long as there's the weak interactions, which everybody has. So that's great. So at least they can be produced. And to detect them, one needs to use, again, the weak interactions. But because of the name, they are really weaker than all the other interactions. They are much harder to interact. So the majority of neutrinos go right through us. And those, let me go to another plot to remind you that these folks had to do huge tricks to be able to capture neutrinos, right? So let's take, for example, the Super K experiment, which is the one that made the image of the sun. This is a humongous bath of water filled with photomultiplier tubes around the big bath of water, the big swimming pool. And here's the snow lab is sort of a rounded one. This is more of a cone looking like. And here you can see the three folks checking PMTs on a boat inside this huge tank. And this is necessary to see the few neutrinos that are going to interact and make a little light. So they are detectable, but they're very delicate. And it doesn't have to be. So the higher the energy, the more they, in principle, interact. So it's easier to see the high energy ones in terms of interactions, but the fluxes are lower, right? So we have to be trading off between detectability and the flux. So for us, the nice piece is that, and for IceCube too, is that at the higher energies, we do get them to come through. There are fewer of them, as this plot shows. So the fluxes are low, of the cosmogenic are very, very low, but also of the astrophysical ones, or if you wish, this plot, right? It shows how we are going here as opposed to the very high flux ones produced by the sun or the atmospheric neutrinos. So it's challenging because the flux is very low of the astrophysical and they don't interact very often. So the majority of them go right through the detector, but they from time to time interact. Now, the ice is a great way to detect a neutrino, not because it's cold, but because it's quiet. So what you want is a very large volume, a kilometer cube, without much light at all. So one can do this, for example, in the South Pole, because there are no city lights, nothing happening that would light up all our detectors. Another way to do it, I don't think I have an image, is to put these kinds of detectors in the ocean. So there is another series of detectors, Antares and now KM3net and others in the Mediterranean Ocean. The French, the Italians, the Greeks, and others are involved, the whole European collaborations involved in putting these detectors deep under the sea, so that, again, there's very little light from human-made light. And so in principle, you could also see this very rare interaction of neutrinos. So it's a long answer, but it has nothing to do with the fact that it's cold. It has to do with the fact that it's quiet, and it is a medium that you can basically, once you generate the light can be transmitted to these photomultiplier tubes. So it's basically a great place to do it, but it isn't a necessary condition.
Perfect. Okay, so it's all about avoiding light pollution and noise.
Exactly, and being able to see the signal, the very, very faint, rare signal. Yeah.
Yeah. Well, actually, I think in the last answer, you've already answered the next question, which was neutrinos and photons are the most common particles in the universe. Do they interact with each other? You've already said they don't.
Not directly, indirectly, but yeah, not directly. Mm-hmm.
Yeah. And then we also have a few questions regarding neutrinos and dark matter. So do neutrinos interact at all with dark matter? And how are they or cosmic rays affected by dark matter?
Great.
And the last one is dark matter more abundant than neutrinos?
Right. So let me start with the last one, which is dark matter is a lot more abundant than neutrinos. And dark matter is more abundant than anything that is matter. So cosmological models that explain the evolution of the universe, that explain what we see best in my James Webb image. So everything that we can explain from this image, including many other measurements, including the microwave background, are all what we call the standard cosmological model. And in the standard cosmological model, the only way we can explain everything is if the universe has a lot more dark matter than it has normal matter, and the normal matter atoms or nuclei, hydrogen and helium pretty much, and then there's a lot of neutrinos too, but they are underdominant even compared to the atoms. And then we have the dark energy. So dark energy is not matter, it's some energy that could be a cosmological constant or some constant amount of vacuum energy all over the universe, and that is 70% of the content of the universe. Then we have 25% of the content of the universe in dark matter, and only 5% left to be everything we know. So all the image that we see here, including all the galaxies, are made of normal matter, and the normal matter is just 5%. So you have to imagine that there's another, 25%, or you multiply by 5 the amount of extra stuff around these light spots, which are the dark matter. So dark matter is something that we've known from the 1930s. Basically, Gzk, looking at clusters of galaxies like this one, noticed that the galaxies moved around, and you can do that through the redshifts, the change in the light due to motion, that they moved around as if there was a lot more mass where they are than the mass we can see. And that's still the case. So, and now we know it's about, 5 times more. And of that, the dark matter, there are a few things that we would like it to be like, right? So the simple answer is we have no idea what dark matter is. However, we have a lot of models, and the best model in terms of popularity and the number of experiments trying to either detect it or rule it out is what we call weakly interacting massive particles. And basically it is a very heavy neutrino, meaning that the only way this particle interacts is again through the weak force, which is like a neutrino, and it's very, very heavy. So of the 4 forces, again, neutrinos only interact through gravity and weak interactions. And we expect the dark matter, we know the dark matter interacts through gravity because that's the effect that we measure. We hope the dark matter particles, if they are particles, interact through the weak force, just like neutrinos would. And so the WIMP, which is this weakly interacting massive particle business, is basically a heavy neutrino version of what we know as neutrinos. But we haven't observed them. There's many searches to try to find them directly as they interact, just like we look at neutrino interactions in these huge detectors. We also hope to be able to see indirect measurements of these dark matter particles interacting, for example, in the sun. So IceCube, which is that the neutrino detector, is looking for neutrinos produced by the dark matter particle interacting the center of the sun and sending neutrinos over, which would be one signature. Another way we could try to find dark matter is maybe through the cosmic ray production of dark matter annihilation or decay. So if the dark matter annihilates with itself, or if the dark matter is decaying after some long time, then we should see that in cosmic rays. So there are many, many searches for dark matter signatures, but so far none of them are totally conclusive. So we don't know the answer to what the dark matter is.
Thank you very much. So we have a few questions relating to the nature of neutrinos. One of them is, how many types are there, and can they turn into each other?
Right. Yes, that's how the gentlemen, the second two gentlemen on my plot got their Nobel Prizes, was to show exactly that. So the first team, Ray Davis and Koshiba-san, these two, or sensei, got the Nobel Prize in 2002 because of the solar neutrino problem. The solar neutrino problem is the fact that if you make a model of the sun using astrophysics and stellar structure and the nuclear reactions that should keep the sun as bright as we see it, there should be three times more neutrinos arriving than what Ray Davis was observing in his first detector of neutrinos, solar neutrinos. And so this was called the neutrino problem, which is where did the neutrinos go? And one of the possible answers is the neutrino oscillation answer, which is that the production of the neutrinos are mostly electron neutrinos, maybe some muons are produced, but by the time they come from the sun to us, or from any other sources, from supernova or from black holes far away, they will be the three flavors. They will be oscillating between the different three options. So the production in the sun is really 1/3 shows up as electron neutrinos if all of them were electron neutrinos to begin with. So a third went to muon, another third went to tau. So that oscillation between them is why the Nobel Prize was given in 2015. And those were was shown by the SNOW experiment led by Art McDonald and the Super K experiment led by Kajita Sensei too. Those two were observing both the solar neutrino issue and the atmospheric neutrinos. And atmospheric neutrinos are neutrinos produced by the cosmic rays, and you can observe it in the other side of the Earth. I mean, you could observe it in both sides of the Earth, but the idea is that you filter the cosmic rays out by looking at upward-going neutrinos on the other end, for example. And then you can do neutrino studies that are very precise, and that's where the oscillations were found. So, the idea of oscillations had been around, but we didn't know for sure. And that proves that neutrinos have mass, and that they have all kinds of interesting properties in the particle physics side. And that's done again with astroparticles in that sense. But these are very low energies compared. So if you look at the solar neutrinos and the atmospheric neutrinos, they are lower energies than the astrophysical and the cosmogenic. But the high energy ones is the ones I'm working on, but these are brilliant neutrinos to do physics with.
Thank you very much. I think the next question you've also sort of touched on. I think the answer was no. Are neutrinos affected by magnetic fields?
No.
Yeah, okay. Can neutrinos be produced in particle accelerators?
Oh, yes. That's how they were basically discovered to begin with, as a neutrino. So the neutrinos, the fact that they oscillate is a more recent event, but the three neutrino flavors were discovered through particle physics experiments in the laboratory. The electron neutrino was, Fermi way back then, when there was basically, reactions that were missing pieces of them, and that's where there was something neutral that was taking away momentum. Either we had to get rid of energy and momentum conservation, or pose that there is another particle that we can't see. And eventually that particle we cannot see was made into a reaction. So you basically have a disappearance of something, then appears again. And that's how one discovered, electron neutrinos. And then the muon and the tau were discovered later. But those are all done in experiments, in laboratory experiments.
Okay, thank you. So we also have a few questions relating to gamma rays and cosmic rays. So how do they differ from neutrinos, and do they have different sources?
Right. So the answer, let me choose this guy first, right? So yeah. Gamma rays are photons, so they are just like visible light, but higher energies. So when we look at this piece here of electromagnetic radiation, from observations with visible light, you get to higher energies as ultraviolet, X-rays, and gamma rays. Gamma rays can keep on going. So it's not just at the scale of a nuclei, they can get higher and higher and higher in energy. And I showed a plot with Fermi spectrum, which shows that kind of extension. And gamma rays are emitted by almost every one of those transient events, and they were actually discovered through gamma rays. So almost all of these things, let me go back one just so that they can dance around. So gamma ray bursts, the name already tells you what it is. It is a burst of gamma rays. And all of these other events, before we known them through gravitational waves and neutrinos, many of these transients are seen in gamma rays or in X-rays. And so that's the high energy astrophysics side of what we do. And these are basically very, very high energy light, right? So if you go back to the here, right? So this is just photons of very high energy, and they interact. I mean, they are produced by nuclei or electrons or any of the things that have charge, which are everybody except for the neutrinos and the Higgs. But that's how you produce gamma rays, right? By basically shaking matter to very high energies. So they are basically a trio, right? Because through the weak interactions, you then produce neutrinos, which is what very high density like neutron stars have, or even just before you join a black hole kind of situation, you also have the ability to produce neutrinos. So this is, again, the gamma rays here that reach 10 to the 3 GeV, so 10 to the, 10 to the 11 or 11 to 12. The same energies that accelerators are reaching almost, and then we have the neutrinos, which are a little bit higher at the PeV scales, and then the EeV scales for the cosmic rays in gray. So we've seen all of these things. The gamma rays are the nicest in the sense that you can basically point back to the source. They sometimes are very close to what the X-ray emission looks like, so you also can look at the visible. So they are much better connected to the other part of the electromagnetic spectrum that tells you a lot about all the sources out there. Neutrinos are likely to be connected to, but so far we've connected just a few of the sources. A very rare event that we could see neutrinos and gamma rays from the same source. And cosmic rays, so far we haven't been able to directly connect them, but we have some hints of what possible sources look like.
Thank you very much. A related question: what is it that neutrinos tell us about the universe that other particles don't, in particular cosmic rays?
Yeah, so a source, so if we take those sources that I played with before, and I'm just going to make the neutron star dance around a little, they are going to produce, just let me go back because it's more fun when they move around. They will produce gamma rays for sure, but they also can produce a lot of neutrinos. We don't know, we think blazars are doing it, both the photons, so gamma rays and neutrinos. We think that neutron star coalescence will also produce a lot of neutrinos. It makes sense because these are two very, very dense nuclei hitting each other. So the likelihood of producing a lot of neutrinos is there, but we haven't been able to prove it yet. Because we haven't seen that. We see a lot of neutrinos, but we don't know where they're coming from. So correlating them, so the sky is filled with neutrinos arriving, and to tell exactly which ones are coming from where, since there's too many of them, we need to correlate with something that is in the electromagnetic side of the cascade or the gravitational side. So one of the goals for the next generation is to have neutrinos and gravitational waves back to here. So doing neutrinos and gravitational wave detection of the same event in the sky. That will be the next cool thing to do.
Okay, so there comes the next Nobel Prize, I guess, possibly.
That would be great.
Yeah, well, actually, there's a question relating to those large projects or efforts for detecting neutrinos that you were talking to us about, that are done by large groups of scientists, pulling expertise and resources together. So how do efforts to detect neutrinos compared to other international efforts such as LIGO to detect gravitational waves or particle accelerators like the CERN. So compared to those large projects, how do neutrino detecting and analyzing efforts compare to that?
Excellent question. So as I show here in this image, the LIGO is in many parts of the world, the LIGO collaboration itself and the LIGO detectors. And obviously for gravitational waves, it's very important to have more than one site because these are tiny little amplitude fluctuations. And if you don't have two detectors telling you the same thing is happening, it's very hard to be trusting of that result, right? So there's the fact that you have more than one measurement makes this one wave that went through easy to determine both that it's real and that it came from some direction in the sky. The more detectors, for example, 3 or 4, you get a better localization in the sky of where it came from. And that's crucial to do these joint things, so to look at gravitational waves and neutrinos, because the original LIGO detection without the extra information will give you a very large part of the sky where these events could come from. And you want a smaller part of the sky so you can point in that direction, both for the light that is produced, but also by the neutrinos. Now, the question is, how big are these collaborations, right? So I think the biggest by far is CERN and the LHC and all the detectors in the LHC. If you add everybody together, is a very large effort in the high energy physics world. In astrophysics, we're getting pretty large too, but of the order of, hundreds. So if you look at telescope array, maybe 100-ish to 200-ish. Pierre Roger was 400, probably now it's 500 or more, and many countries. So those are some of the things that we've been growing. And then IceCube is a large collaboration. It was mostly US and Europe, but now it's getting much bigger as it proposes the next generation, which would be generation 2. So IceCube Gen 2 is the next version of extending these detectors to much larger volumes and also improving the types of techniques. Unfortunately, I didn't put one slide I was hoping to show, which is many, many different ideas on how to look for neutrinos. So we have one of them. There are others which are looking with balloons, but with radio antennas instead of Cherenkov type detection like we're doing. There are folks putting radio antenna on the ice, radio antenna in the ice, and then optical modules also in the oceans, as I mentioned. So there are many different groups. These are more modest compared to the LHC, but at a reasonably large scale also. Many countries involved, and I think that, as you said, brings resources together, but brings teaching and knowledge and exchange of ideas and creativity among different parts of the world. So it's really, I think, a great pleasure for me to be part of these, have been part of these collaborations, and have met people from 19 countries working together for Roger, 16 countries working together for the GEMUSO collaboration. And I think it's been a very wonderful partnership across the board and different expertise. And I think it's good for all the different countries that are working together. So we are of the 100 scale. One of the challenges we have as we really rely on international collaborations, which I think is the best thing for science, is that from time to time we have one detector like the one we have in the space station developed with Ukrainians and observed with Russian colleagues, and developed by Ukrainians and Russians, and now currently in the Russian module of the space station. And so challenges on the planet of geopolitical flavor make some of these collaborations trickier than they were in the previous incarnation of our relationships. And so I hope we go back to having this very free exchange of ideas and respectful way of handling all kinds of interesting questions in science, including in our introduction, the question of the planet itself and sustainability and all these other challenges that we as a generation and the future generations have. So, but it's been a wonderful partnership. In the ones I've worked with, these large things are a bit scary, but they are usually organized so you have about 30 people that you meet every week. So I have weekly meetings with about 30 that keeps pushing things, but those 30 have another 30 each, so it's easily extendable to more folks involved. So it's been a wonderful ride, and I think it's been very helpful. We have very large ambitions in astronomy, optical astronomy, for example. The next generation telescopes are very expensive projects. They are starting to reach not quite LHC scales, but not CERN scales, but almost there, right? $1 billion scales. So those things on the ground. In space, we definitely beat the high energy physics with James Webb, $20 million in one telescope. So, things are challenging, but I think we are so proud of being capable of learning so much from the universe that we should really use our resources to continue to investigate and learn more about our home in this universe.
I think it's a really nice message, and I guess it's one of the downsides of large global efforts in science is that sometimes politics can get in the way, and but I guess the benefits outweigh the negatives, and it's one of the tiny forces that pushes together rather than pushes apart. Angela, many thanks for this excellent talk. We're not done yet with the questions. The last one is, what would you say to a little girl or a little boy who's looking up to the stars and wondering, is there anything left to be found out? And if there is stuff still to be found out, what would you tell them so that they can become the next scientist, contributing to these large international efforts and shaping our knowledge of our universe?
So I would say first that there's a lot of questions, so no desert there, meaning the more we learn, the more questions we ask, which is why science I find to be a brilliant option of choices in of careers, because there's always new questions to be asked and answered, and then the next one kind of show themselves. And this is why collaborations are very helpful, because you can move faster, but also I think be curious, right? I think there's no, the younger we are, the more curious we are, and then we learn to be less curious to, try to get things done, as opposed to just asking questions nonstop, which kids are really good at. I think we should keep on asking questions. We need to be conscientious of the questions we can't answer in our own lifetimes, and questions that might be taking longer than that, and questions that can be very fastly answered. The other piece I would say is be aware of the questions that have been answered, right? So the reason why we go to school and we study so hard is because many people before us have asked questions and they got the answer. So we need to learn what those answers are so that we can ask a new question faster. So for that reason, it's very important to me to study. Worst case scenario, you can have a great job independent of the science you learn, but the more you can study the things that give us the basis for science, so mathematics, the history of science, how physics works, how engineering works, how astrophysics, biology, chemistry, so many new areas and important areas being developed. We talked about the pandemic having one positive effect, that we could do the Zoom meetings across the globe. We got vaccines developed so fast. It's unbelievable what our colleagues in the biological side, the medical side, have been able to do. So I think we are very proud of the power of science, and studying science, any science, is, I think, a wonderful thing to choose. My own subfield is, trying to understand big questions about the universe, but also about the smallest things, the particles, so the big telescopes and the big microscopes. But we have many, many questions related to any of the pieces that we pick that might become worth somebody's life dedication. So I think finding the questions you want to answer is what I would spend time doing.
I think it's very important never to lose our curiosity for the things that happen around us. Well, thank you very much, Angela. I think it's been a privilege to learn today so much about the efforts to detect these particles and use them to better understand how the universe works around us. And it's fantastic to have someone who is part of those large collaborating efforts on a global scale to tell us about how they work and the new questions that are awaiting to be answered. We are also very grateful to all the UNAM representations around the world as well. Many of them retransmit our talks from week to week. And today we have the privilege to have Alberto Fonserrada from UNAM Chicago. So if you want to say a few words, and also if you have any questions for Angela, I'm sure that she will be happy to answer them.
Thank you. Thank you very much, Araxi. Well, in lieu of time, I will keep my comments short, but I just want to thank Angela. We're very proud of this partnership we're developing that keeps growing with the University of Chicago. That was a phenomenal talk you just gave. And you said it towards the end of your talk, power of science. And we're totally committed. As you know, we're part of the international network that UNAM has abroad, part of the 13 representations abroad. So in Chicago, we're very, very happy to, and we feel pretty privileged to be in that, in the Midwest, where all these things are happening. And I just want to say thank you to the Fundación for inviting us, for including us, Araxi, Jaime, Dionisio, everybody. On behalf of our director, Guillermo Pulido, who's flying just now, he couldn't join us, but he sends his best regards. And hopefully this is one of many. Thank you very much, Angela, for a wonderful talk, and we will be in touch.
Thank you. Let's meet in 3 dimensions.
That would be great. So to close this session, we have a few words from Dr. Jaime Urrutia, who is a member of the advisory group to Fundación UNAM and also a member of Colegio Nacional in Mexico. And then we'll have a few words from the president of Fundación UNAM, Dionisio Meade.
Thanks very much. And interesting how research at so different scales connects. Well, how cosmology can combine with particle physics at the biggest, the largest scales to the most small ones. And it's also interesting the new analytical capabilities to observe, to detect, to collect new data. Thanks very much, Angela. And the new facilities and these large missions with the new detectors, the LIGO, the James Webb, all of these particle detectors, they provide us with a new view of the universe. And the title you choose for the conference, this new messengers, yeah, it's new windows to look at the universe. Thanks very much, and we look forward for having a close collaboration with the University of Chicago. We have a lot of students in Chicago, and we look forward for joint projects. So thanks very much and congratulations. Parabéns.
Muito obrigada. Muchas
Muito
gracias.
obrigado. Conferencia interesante. Yeah, we look forward for having the opportunity to meet in 3 dimensions. That will be great. Muchísimas gracias a todos los que nos acompañaron, los que nos mandan saludos de diferentes lugares en las sedes de la universidad, incluyendo Chicago, Arizona, Texas, Londres, y también los que tenemos conectados de la parte de Brasil, Argentina y Chile. Muchísimos saludos a todos. Y muchas gracias, Araxi, y le pasamos la palabra a nuestro presidente de Fundación UNAM. Parabéns.
Muchísimas gracias, Ángela, por esta pues, presentación tan motivadora y tan inspiradora, tan motivante. Hemos pasado del mundo del Hubble al mundo del James Webb, en donde vemos pues la dimensión inacabable del universo, pero hoy nos adentramos a algo mucho más pequeño, al mundo de los neutrinos, que casi apenas se puede inferir pues de manera abstracta, porque es muy difícil capturarlos, es muy difícil cobrar conciencia de su existencia, pero ese es un mundo que es de una sustancia que, según se dice, es la segunda más numerosa del universo. Yo creo que invitar a los jóvenes, y ese es un poco el sentido de esta despedida que quisiera hacer para participar en este mundo formidable de la ciencia, pues con algo que para que quienes hemos tenido la oportunidad de vivir en esta época es tan reciente. Apenas se dice que en 1956 se pudo inferir la existencia de los neutrinos y hoy sabemos mucho más de ellos, con sustancias mucho más pequeñas pues, que cualquiera de las moléculas que nosotros hubiéramos podido imaginar. Así que adentrarnos en ese mundo que nos está diciendo a los jóvenes, vengan conmigo, vengan con Ángela a estudiar, a investigar, a conocer más sobre este mundo que nos ofrece horizontes tan fascinantes, pues es algo que nos ha motivado mucho, nos ha llamado mucho la atención y que quisiéramos que en este cierre, en este año internacional de las ciencias básicas, en donde nuestra fundación ha tenido un papel tan relevante y se ha sentido tan honrada, tan estimulada por haber participado en la realización de este evento, por haber sido considerada como representante de nuestro país, pues que tuviéramos como cosecha de este esfuerzo muchos más jóvenes que se interesen por este mundo. Aquí hemos visto que es inacabable, que es prácticamente infinito, que así como se ve lo enorme del universo a través de estos telescopios recién instalados, pues también hay un mundo mucho más pequeño, un mundo que apenas se puede inferir su existencia, pero que explica tanto, como aquí se ha dicho, de los mensajes que recibimos del universo y a través de los cuales podemos conocerlo mejor. Y conocerlo mejor también nos invita a protegerlo más. Muchísimas gracias, Ángela, muchísimas gracias, Araxi, gracias, Jaime, gracias, Alberto Fonserrada, y pues yo creo que lo que nos ha dicho Jaime acredita esta presencia pues ya tan extensa de tantos países que se interesan por la ciencia. Para el conocimiento de la ciencia no hay fronteras, desde el universo no se reconoce ninguna, y yo creo que ese es algo que nos convoca a sumarnos todos por algo que es un valor superior, el valor del conocimiento, el valor de la ciencia y su aportación a las mejoras en las condiciones de vida de la humanidad. Muchas gracias, Ángela, por esta presentación. Muchas gracias a todos y pues los seguimos convocando a nuestras pláticas de este consorcio de universidades por la ciencia, que como aquí se puede acreditar, se presentan investigaciones en curso y se convoca a los jóvenes que quieran estudiar que quieran hacer su maestría o su doctorado, a tratar de involucrarse mucho más en este espacio de la ciencia que hoy nos ha hecho favor de compartir Ángela con su formidable presentación. Muchas gracias a todos y muy buenas tardes.